to my office before. A student caught me in the hall. She's a former student, and she's now at Stanford. And she had a scholarship opportunity and wanted to ask me to write a letter of recommendation. Sure, I'll do it, or to be a reference for it. So I thought that was it. Okay, I can eat lunch. No, she had to come in and tell me everything she'd been doing, which is fine. I appreciate it. Enjoyed hearing what's been going on, except I only had less than 45 minutes for lunch, and she took 35 of those 45 minutes. So, but it was good. It was good to see her again. I wanted to eat. Man, I just barely got my salad scarfed down. Okay, the thing I wanted to make sure that I got on here, please do the student course evaluations. Have you already done them, by the way?
I did.
You did.
But they sent me another email to do the vote for the teachers, something like that.
Okay. The what?
Voting. Like, am I pronouncing right?
Yeah.
The vote for the teachers.
Something for the teachers.
Vote.
Work study for the. No.
VOTE. Vote.
Oh, vote?
Yeah.
Really? Okay. Wow. I don't know anything about that. I know they had said they were going to have something, but I thought that was going to be like a month ago or something. I thought that was already done. They must be doing something new this year. Okay. These are things you set up. Oh, Student Government Association elections. Okay. Okay. This is just asking you to do that.
Yeah.
Yeah. Now down here, okay, you've already completed all these.
Yeah.
Okay, yeah. Those are the main things you have to do. They would like you to vote for the student government if you choose. I mean, that's. I never say don't vote because I believe in voting. That's a big thing with me. I've always, ever since I've been eligible to vote, I want to vote in every election. I have missed a few that, just not big ones, but things I didn't even know they were having, or I spaced out that day or something. But I always vote any chance I can. So I encourage you to do as well. But student government's not. Okay. But those people do work hard, so you'll see some of their ads around on the walls. Mostly on the Birmingham campus. I don't see nearly as many out here. I don't think we can so much. I didn't say that, did I? Okay. This campus is sort of, let's just do the work and go home. I mean, it's a lot more, just get it done, get it over with. The other campus more time. Never mind. Okay. Any questions on anything before we get started today? I realize I have two arrows here. I think we got started with higher order partial derivatives, didn't we? And were we right at the point of doing example 7? 761, yeah, on example 7, right? Yeah, because I had a mark last time I taught this on page 760, but I thought we had already done that. Well, here's my thing here. Yeah, we hadn't done Clairaut's theorem yet, but I told you about it, and but we're going to do example 7 at the top of the page, 761, or near the top. Okay. No questions before we get going? Okay. Yeah.
Oh, yeah.
Okay, what's the question?
When are we going to give the final exam?
Yeah, I was ready for you. Knock on the wood on Wednesday.
On Wednesday?
Yeah. Because, you need yours early. When do you have to have the file?
If I can get today and I can work on some of the questions used tomorrow, and then after Wednesday, I got I'm flying 30th.
Right.
So, but I don't want to work on the test on especially I'm flying
Okay. Well, let me look and see if I can piece together a test for you out of tests I've already given, and I'll see if I can get that done.
And this one and the
And
differential equation.
Yeah, differential equations. So right after differential equations, get with me and I'll see what I can do. I've got differential equations ready,
Okay.
but this one, because it's going to be pieces from different chapters, I've got to piece those together. And I was wanting, I forgot you had needed it earlier. I was wanting to see how far we got before I put the pieces together. So, yeah.
I try to get everything done with the school by Thursday.
Okay. Yeah, I'll try to get it to you then. And I mean, right after class, differential equations class, I'll try to get something for you. It might be in pieces, like I said. I may have a page out of this test, a page out of that test, a page out of this test, and you do this problem, this problem, something like that. Okay. And I'll have yours worked up then for Wednesday. Is that okay? You don't have to.
When do we have to have it in?
Anytime next week.
Anytime next week?
Yeah.
Until Friday?
Through Friday if you need it. Sooner the better, but through Friday if you need it. Now, Friday I'm on Birmingham campus, so I'll need it. Take it over there if you're going to turn it in Friday. Okay. All right. Sorry, I knew you needed it, but the end of the term is swept up. Here's one of the things that it was really disappointing to me. I have been looking every week for more than a month, about a month and a half, for fall schedule so I could get it done. And they never opened it. They never opened it. They never opened it. They finally opened it last week and said it's due Tuesday. And fall schedule is a big schedule and takes a lot to do. And I've got most of it done, but I had so many things going on Friday. My boss was not in the office, so I had to cover students who came in to see him. And so I was just stacked all day Friday. And so I got most of it done, but not all. And I hope to do some over the weekend. I got some done, but not as much as I intended. So I've got to have it finished by tomorrow. So that's why I hadn't done any more. So this is what was turned in today so far. And this was stuff that was turned in late Thursday so far. So I haven't had a chance to do any of them because there are a couple at the back there that I did get to do because in between class time, do one or two pages at a time. So it's gotten crazy for me too at the end of the term. Otherwise, I would have had the things ready, I think. I don't know. Okay, let's do example 7, page 761. Calculate the second order partial derivatives, partials of, okay, f of xy is equal to x cubed plus y squared e to the x. It says calculate the second order partials of that. Guess what we got to do before we can do any second order partials? First order partials. Because you can't take a second until you have a first, right? So let's do the first orders first, okay? Which you want to do first. Say again?
Do we have to do x and y?
Yes, you do.
Oh, okay. Let's do
Y first? Okay. Why not? Okay. So F sub y is what? No? Okay, we're taking derivatives. 2x, oh wait. Huh? Okay, all right. You said with respect to y, right? Okay. With respect to y, then you count the x's as if they're constant. And the derivative of a constant is 0. Okay, so this doesn't contribute anything to F sub y. So let's go to the second term. What do we do there? Second? 2y. Not all. E to the x. Why? Because you treat it as a constant. So basically, your 2 and the e to the x are both sort of like constants, and y is your variable. So when it's by itself and taking the derivative, that's 0. But if a constant times a function, you still have the constant in there. Okay? So there's your f sub y. Okay? Now, we could, from this point, do our second partials with, now that we have the f sub y, or we can do the f sub x and then do them all. I don't care. What you want to do? A little louder? Okay, so let's do f sub. And which one you want to do now? The first one's going to be y. What's the second one going to be? Yes, we are. It says do the second partials. And second order partials, that's all of them. So which one you want to do first? Y? Okay, so f sub y. Y not. Okay. What would that be? 2e to the x. Fantastic. The other one? Okay, f sub yx, is that what you're doing? Okay, and that would be what? Now go back to this one, yeah. What would that be? 2y to the x, perfect. Okay, you see why? Going back to f sub y, taking the partial of that with respect to x, 2y is counted as a constant, so bring it down, derivative of e to the x is e to the x. Okay, next. F sub x, the partial of f with respect to x would be 3x squared. Say again? Plus y squared e to the x. Perfect. The 3x squared causes the derivative of that. The second one, count the y squared as a constant, and the derivative of a constant times e to the x is a constant times e to the x. So yeah, same thing. Now, what next? What next? XX, f sub xx. The second partial of x with respect to x squared is how you could say that, okay, if you wrote it the other way. Okay, and what would that give you? 6x, success, okay, never mind. Y squared e to the x. That's getting old, isn't it? Okay. Next, f sub xy. That's the second partial of f first with respect to x, second with respect to y. Okay? And what would that be? And again, go back to f sub x to get this one. 2y e to the x. Now what do you notice there? F sub yx and f sub xy are identically the same. Okay? Yeah, but your f sub yy's and f sub xx's really have very little to do with each other. Nothing in common. All right? Now,
So
yes.
how do we get the x? I'm sorry, xy again?
F sub xy, this one?
Yeah, x sub xy. Yeah.
Okay. You start with the f of x, take the partial of that with respect to y. So the partial of this with respect to y is 0, because there is no y in it. So it's just like a constant. Okay? And then you take the partial of this with respect to y, your e to the x is a constant, and 2y times that constant. Right? And then you notice that's the same as this. Okay? Good deal. Now, one more before we get to Clairaut's theorem, and this will be example 8. And fortunately, I read it before I did anything. It says calculate f sub xyy. It's almost like the Philadelphia radio station, f sub, what is that one? WXYY or something like that, or HYY. Yeah, I think that was WHYY. Why? Okay, never mind. So, what is partial F with respect to X with respect to Y with respect to Y? Where would you go?
Where you have the partial derivative.
Yeah, let's go to the one we just did, that last one we did. Take the partial of that with respect to Y. And what do we get? Two. No? 2e to the x. Perfect. Okay? And that's exactly what they got. Good for them. That's why I'm glad I didn't erase the board before I read the problem. Otherwise, I'd have had to go back and do all that. See how it works? So really, partial derivatives are pretty straightforward. You just do you got the function, you take the partial with respect to it, just one variable at a time, and you just do count all the other variables as if they're constants, take derivative of the one that you respect to, and carry it on through, and then do as many ways as you want to. All right, now we're ready for Clairaut's theorem, and what I think I'll do is first erase this line, and then I'll blow it up. Can't say that too loud. Homeland Security will come and get me. All right. Here's Clairaut's theorem. And by the way, let's see, how is this class doing as far as all but one student has turned in the paper, and that student isn't here, so way to go. I don't have to worry about papers. But if that student's listening, Clairaut would be a good paper topic, or how in the world Clairaut came up with this theorem. That would be one, or applications of this theorem. There's various opportunities here. But here's Clairaut's theorem. Equality of the mixed partials. What we just noted above is that Marcus is here. First class of the day would be more than half the students here. This morning's class was 2 out of 4. This later morning class was 2 out of 4, and this one was 2 out of 4, but now it's 3 out of 4. Way to go. So here's Clairaut's theorem, equality of mixed partials. If f sub xy and f sub yx are both continuous functions on the same disk D, then the f sub xy evaluated at AB in that disk, and f sub yx evaluated at AB within that disk. Those two are equal for all A's and B's in the disk D. In other words, the second partial of L first with respect to X and then with respect to, actually, when they write them this way, it's the second partial of L first with respect to Y, then with respect to X. Because when you take the partials this way, you're taking the partial with respect to X of the partial with respect to Y. So you did that one first and then this one. And that's the same as the second partial of L with respect to first X and then Y. As long as X, the f of xy and f sub yx are both continuous functions. If they're not, you can't use this. And that's sort of what they talk about in the margin. The hypothesis of Clairaut's theorem that f's of xy and yx are continuous is almost always satisfied in practice. But there is an exercise 84, which you won't have to do because it's even, for an example where the mixed partials are not equal. And if you want to pay special attention to that, you can. All right. Now, I had indicated we were going to move off of this and into integration, multiple integration, fairly quickly. So do you want to skip these other two examples? They are actually 3 examples. They're really good examples, but I don't want to rip off time that we need for other things. What you think? And there's a picture of Alexis Clairaut, brilliant French mathematician, presented his first paper to the Paris Academy of Science at age 13. Can you imagine it? Okay. You won a prize for an essay on lunar motion that Euler praised surely an exaggeration is the most important and profound discovery he had ever made in mathematics. Probably a little bit deep there. What you think? Those three, or move on? And I know all three of you have turned in papers already, but here's a historical perspective on Joseph Fourier, another brilliant French mathematician. He was also sort of a revolutionary of sort. He was one of Napoleon's buddies, so he was involved with revolution in some ways. And then Adolf Fichte, a German scientist who did Fichte's law. So either of those would be decent paper topics. So have y'all decided you want to do those three examples, or move on? Huh? What's that? I don't think you'll need these particular ones, but they're just more practice. And they're in the book, so you can practice them in the book. Okay? All right. Now, only because this is some pretty important stuff, what I'm going to do, there's Clairaut, I mentioned him. Here is the plot for I think example 10. No, I believe this may be the plot for 11. It is, and this is something, example 11 is very much both 9 and 11 are really practical applied type problems, especially 11, the heat equation. And you can see it's a pretty hairy equation. You have spatial variability and time variability, and that's what this is showing. Here's your spatial variability. You have a metal bar here heating the center, and you watch how the heat is dissipated spatially and with time, and spatially and with time. So you see how it moves from there. It's a pretty good illustration and a pretty good problem, so I would pay some attention to that. And then this is part of that heat equation. I will blow it up for you so it's a little easier to read. But this is a partial differential equation. It just doesn't show up in heat. It shows up in lots of areas. Part of my research on my doctoral program was movement of water through a swelling soil. So not only was the water moving downward, the soil particles were actually moving upward. So you had lots of motion going on there, and we were using dual gamma radiation attenuation to measure both bulk density, which is the soil particles, and the water content, which was the water flow. And the partial derivatives got to be hairy, and this was fairly typical of some of those. You had variability with respect to displacement, and you had variability with respect to time. Typical, very typical of what you find many places in physics. Okay? Now, I don't want to take too long doing this, but I feel like I really ought to at least expose you to some stuff here. So this is going to be quick and dirty. You're not responsible for this part. What you're going to be tested over is through 14.3. But let me just show you a little bit of 14.4. I don't know why it's not coming up. Sorry, we got started late, and now the thing is being it's not opening. Okay, what I'm going to do is go back and close that. There's something wrong with PowerPoint. It just seems like there's always something wrong with PowerPoint. Okay, I'm going to close that. Okay, so now I've got to go in and restart all this again. Sorry about this. Four. Again, we're not going to dwell on it. I don't know. Maybe this just isn't going to. No, there it comes. Okay. Slideshow from current slide. All right. Remember when we did integration to begin with? Well, derivatives. You had a curve, you took a derivative, it told you about the tangent line, right? Slope of the tangent line. Well, guess what? With a spatial function, two or more independent variables, you have a surface, and you take a derivative of that, it tells you something about the tangent plane at a point. So it's just a step up in both dimensions. A curve is a two-dimensional thing. A straight line is a one-dimensional thing. Here you have a surface is a three-dimensional thing, and its tangent plane is a two-dimensional structure. Okay? Doing that kind of stuff. So that's what differentiability and tangent planes, that's what this section's about. Now we're not going to do it, but here we're going to talk about locally linear things. That looks like a wadded up piece of paper, right? Can't you talk about derivatives there? Well, you can if at a point, if you take this and keep blowing it up and blowing it up until it gets so it's almost planar at that point, then we call that locally linear, even though in this case it should be locally planar. But anyway, that's the concept here. As long as you can do that, you can take these partial derivatives. Okay? The equation in fact, I guess they don't show the equation in the new edition. So I'll go over that. De Silva will have it in hers. Shows up there. Here is the figure at the bottom of the page in our book on page 768. It shows the tangent line if you take the partial with respect to x at a fixed y value, you get that tangent line. If you do the partial with respect to y at a fixed x here, you get that tangent line. The plane that's defined by those two lines is your tangent plane. Okay? And then they do some about the error. I'm not going to do too much with that. Here is the differentiability definition. Now, I'm not going to blow it up. It's in your book. You can read it. It just talks about that. Let me give you a real quick and dirty here. This is just basically saying this is the local linearity that we were talking about before. If a function is differentiable, if it's locally linear at a given point, and then that's approximately the z value is going to be the alpha value b, that's the z value, but then if you have a little bit of change of x, like a, and the partial of alpha with respect to that in that direction, partial of y with respect to b, with respect to the partial of alpha with respect to y in the b direction, offset a little by b. This gives you the function a, b. This moves you along past a on the x, past a on the y, and you're given a planar approximation for that value. Okay? Sort of the same type stuff that you did back with linear approximations. Criteria for differentiability. I think if you think about it, you'll realize this is very similar to what you had in a curve. And tangent lines. If f sub x, xy, and f sub y, xy both exist and are continuous on the open disk, then f of xy is differentiable on D. Okay? So the first partials must exist and be continuous on the open disk. Okay? For differentiability to happen. Here is sort of an example of that in a this would be a parabolic sheet, you might say, a parabolic cylinder. Sounds sort of contradictory. Cylinder made up of a parabolic shape, but offset, in a certain way. But on the surface at point P, you can take the partial with respect to x, the partial with respect to y, and find the value of P and use that formula we just had to find the tangent plane at that point. And that formula that we had just back here gave it to us. Okay? And again, you're not responsible for this now. Are there any such shapes that you can't take partials? Yes, there are. For instance, this is a bizarre looking thing. Here's the function here. And you're going to see if when you zoom in and zoom in and zoom in, do you get any close to local linearity? And the answer in this case is no, okay? Because you have your function is 0 at this line here that bisects the xy axis here. It's going all sorts of different directions at different points. The partials don't have a convergence anywhere, as you see here, so the graph does not appear any flatter as you zoom in toward the origin. You still have some places that are straight lines, some that are going up, some are going down. You don't have any continuity. Well, you have continuity, but you don't have equal derivatives anywhere as you're approaching the origin. Okay? So not all functions you can take partials of. Here is a cone that we saw in 12.6, at least half of a cone, and you can look at that. It certainly wouldn't be differentiable at the origin, because here, the derivatives here, they're all going to some value, but here is not even defined, because there is no, if there is a tangent line, it has to be those planes that wouldn't be equal to the other. So that one would not be differentiable at the origin. Everywhere else, yes, but not at the origin, though. Okay? Here's a tangent plane that you think of tangent planes as not intersecting with the surface. They're tangent to the surface. Well, some surfaces you can't help but be intersecting with. Sort of like, I can't write on here, but if you can imagine a function that's changing rapidly here, you see a slope of a tangent line, it's tangent at this point, but it's going to intersect maybe at several other points. No problem. But this is one, the tangent plane to the surface that passes through that. It's tangent at that point, but it's, let's see, below the curve, below the sheet here and here, and above the sheet there and there. So it intersects the sheet in a couple of places, but it's still a tangent plane. Okay. Then here's some local linearity type stuff, so I'm not going to do much with that. Boy, a lot of it too. Linear approximations and differentials. Let's see where that figure is. Oh yeah, that's the here. So there's lots of these formulas, but we're not going to do much more. So that's just wanted you to see and hear some of the nomenclature there. This is what you really need to okay. Let's see if it will do any better this time. this is the stuff I really wish we'd had time to do, but we took time doing infinite series, and that at the beginning, which should have really been in the previous in Cal 2. But here's a definition, and this is something you really do need to know, and it is an interesting concept how it's done. It's called the gradient, and I don't know if you've seen this symbol on calculators and stuff like this, but the gradient of a function, f of x, y. Now notice this function is a scalar function, f of x, y, not a vector function. At some point p, a, b, that's just a point where that function is defined, okay? The gradient of a function at that point is a vector, okay? And here's what the vector is. This upside down triangle, I guess you would call it, is called the del function. This del of f at p. So it's a gradient function, it's a vector function of a vector operator of a scalar function at a point p is defined to be angle bracket. Now, both of you are in the linear algebra class, and when we got to this morning, I told you that book is the only book I've taught from in recent years that did not use angle brackets for vector notation. They use parentheses just like ordered pairs. So this is angle bracket, so this is a vector. It's the partial of f with respect to x at the point AB, comma, the partial of f with respect to y at the point AB. This is the x coordinate of this vector, this is the y coordinate of the vector, and those are, this is a 2 space. In 3 space, it's this one. The del f of the gradient of f at p, again, gradient is a vector operator operating on a scalar function at a single point, is the x component is the partial of f with respect to x at the point ABC, that point P, ABC. That's the x coordinate. The y coordinate is the partial of f with respect to y at that point ABC, and the z coordinate is the partial of f with respect to z at that point ABC. That produces a vector, a 3-dimensional vector, because this is a 3-dimensional function, a function of 3 variables. So you would have 3 components of the function. So a gradient is a very important concept to know. I wish we had time that we could have worked some problems with it. Okay. Speaking of working problems with it, we don't have time to do them, but I'll just sort of indicate fairly quickly what you would be doing. It basically gives you the direction of maximum increase at any point. Okay? And since this, when you look at this surface, think about that surface, that's going to be z is equal to x squared plus y squared. So z, excuse me. Sorry. Sorry, I can't get my throat clear. Okay, f of x, y, independent variables x and y, dependent variable f or z, if you want to think of it as a z. But this is x squared plus y squared at several points, and these vectors aren't drawn to scale because the further you get from the origin, the larger they are. So this is not something that's really a true mathematical model. Usually it goes the other way. So, but anyway, you see that pick any point you happen to choose, and you're going to have a vector that's pointing away from the origin, and that gives you you get that from your gradient. Okay. Here are properties of the gradient. I won't go into those in detail, just saying it quickly this way. Have 2 scalar functions, the gradient of the sum of the functions, that's the sum of the gradients of the functions. The gradient of a constant times the function. This is then the constant times the gradient of that function. Product rule for gradients. Now this one is pretty important because you're dealing with vectors. That would be the first scalar function times the vector gradient of g, f times the gradient of g. That's the vector. This is a scalar, so you're multiplying a scalar times a vector. You're multiplying each component of the vector by the f function plus g times the gradient of f. So again, you get a vector here, and then multiplying a scalar by that, and those will have chain rule for gradients. If f of t is differentiable function of one variable, and that f of t comes from a scalar function that's more than one variable. So you have little f of x, y, z is a scalar function. Okay? Capital F of that value, whatever the f of x, y, z is, that's a single dependent variable there. This capital F operating on that value is also a scalar function. But you're doing the the gradient of the bigger function, the outer function of the inner function. That would be the outer function, the first derivative of the outer function, times evaluated at the inner function, times rad f, which is a vector function of that scalar function. So you do come up with a vector here, but this is like a big coefficient of that vector here, which may have values there too. I'm sorry, this is awfully quick and dirty, but that's taking the chain rule for gradients. Okay? And then here's some examples of what you could do. This is a chain rule for paths, is what it's talking about. And it's in this section that I found it really is interesting how they approach it. They start talking about paths, and they give them variables. They bold the variable as if it's a vector, but it's not a vector. It's just a path. But then when you take a derivative of it, it becomes a vector. So it's rather a strange thing. And next thing you do here is chain rule. Just a little bit of, this is exactly what I was saying before. Your path, and they put a bold C here as if it's a vector, but they represent it as a point. Okay? And it's a path whose curve is a vector function, but it itself is not. But when you take the first derivative of it with respect to t, for instance, then you get a vector function. Okay? So the original function is a scalar function, except they make it how to say it. The path they indicate as if it's a vector, but they're scalar coordinates, not components. But when you take the derivative of it, you get a vector function, and its derivative of those coordinates are now components of the vector. So it is a bit bizarre. But it works out well, but it just, their nomenclature, I think, leaves something to be desired. Okay? They have an example here of Chloe riding a bicycle. No, Alexi's riding a bicycle, so I'll let you follow that. And here's the chain rule for paths. blow it up first, but I'm going to do something here. So f is a scalar function, c is a path. Both of these are differentiable. Okay. Then the time rate of change of the function along that path is defined to be the gradient of the function evaluated at the location in the path times the, and that's the dot product, by the way, the first derivative of that scalar function, that, that then is a vector function as well. A gradient's a vector, and the derivative of the path, even though the path is not a, these are scalar functions, okay, even though that is a vector looking thing, but the gradient of a scalar is a vector, and the first derivative of a path is a vector, okay? And if you're doing that, the d by dt of the independent variable here, that is your gradient of f, which usually has multiple, has to be a gradient, multiple components, and this has multiple components as well, x of t, y of t, z of t, and you would go and do that. Explicitly in the case of two variables where c of t is just x of t, y of t, no z of t in there, then the partial of f, the derivative of f with respect to that independent variable parameter t of f evaluated at that curve t would be the partial of f with respect to x, that's your partial of this, and then times the partial of f with respect to y, that's the y component of this, so this vector has two components. Dot that with x prime of t, y prime of t here, and what you have is, and you're dot product those together, which by the way gives you a scalar, okay? Scalar function, scalar path, derivative of that is the same as and you would expect a derivative of a scalar function of a scalar path should be a scalar, but here it becomes a vector gradient of a scalar function at that path, dotted with CFT. And if you think about this, it's chain rule. The derivative of this, which is the gradient of that function, okay, evaluated at this place, times the derivative of the inside, but this is a vector, that's a vector, so that times is now a dot product, but then when you take a dot product of two vectors, you get a scalar, so sure enough, this thing produces a scalar, but it does it in an intermediate dot product sets of vectors. So when you break those down to see what they are, it's this times that. Remember how you multiply, do a dot product of vectors is first component plus second component, and you add those together. So partial of alpha with respect to that dx dt plus partial of alpha with respect to y dy dt. See, these are regular derivatives, these are partial derivatives, and that's what you get. And sure enough, when you look at it this way, it looks like the dx's and dy's cancel out, and that gives you partial of alpha with respect to t, which is what you're looking for here. Partial of alpha with respect to t as a scalar value. Some sort of interesting stuff. They really are sort of fun to play with. We just don't have time to play with them. Here's actually this looks like an intersection of two shapes, but they're just given here as this function, and you figure out where the various things are going. The gradient vectors and the path, and you're figuring out what the product basically of those are. Okay, here's another one, a directional derivative that we here are defining. Okay. Goodness gracious, I can't get this to move Directional derivative in the direction of a unit vector u. Now, when I write unit vector, I put a caret over the top. The general ordinary vector, I put an arrow because I can't write in bold. But here I put a caret on top, you know, the mountaintop looking symbol. That indicates it's a unit vector. At the point hk is the limit, assuming that it exists, of directional derivative in the direction of this vector u, this unit vector u, of the scalar function f at p, okay? And that would be the unit directional derivative in the direction of u of this thing, AB. P is the point AB. So those are saying the same thing. This limit as t approaches 0 of alpha A plus TH, H being the component of that unit vector that you're wanting the direction of. So that becomes your incremental change in F, the x component of F, and then the B plus TK there, minus alpha of AB over T. And you're letting T approach 0. That's how we define the directional derivative in the direction of unit vector u. Especially when this is so small, I can barely make it out. All right. This is sort of play here now. Now we have a directional derivative in the direction of v of a scalar function alpha of AB, and that's going to be the partial of alpha with respect to AB times your directional vector to E. Okay. Now, don't want to spend too much time on this. So I think I'll just go on. Okay. Yuck. I think these are more parts of the problem that really are going to be a little hard to generalize, so I think we'll just keep going here. See the figure. Okay. Since we aren't doing much more with directional derivatives, this is one way to compute them, so I'll let you take a look at that. I like going through these in a lot more detail. We just don't have time now. Oh, here maybe. This is something. This is more physics related too. You have this scalar function F at this point P. Scalar function has a value, but it has a direction. The directional derivative of that scalar function at P in the direction of u would then be the magnitude of this F del F. You actually calculate del F, which gives you a vector. and then take its magnitude, which is a scalar, and then multiply it by the cosine of the angle in between. Now that is pretty reminiscent of a dot product. It's just that you don't have another thing to be a dot product to. Well, that magnitude of u would fit the bill there. So it's the magnitude of this times the magnitude of that, which is 1, times the cosine of the angle in between. Sure enough, that's your directional derivative. Again, we don't have time to work on these. There's Chloe, or what's her name, riding the bike again. And there's not a lot of time to do this, so I won't go into much here. But it's a contour map. The gradient of F is orthogonal to the level curve through F. So if this is your level curve, your gradient is always perpendicular to that. Okay? So you find that point, find the line on it perpendicular to that. Will be the gradient. Goodness gracious. And one on the interpretation of the gradient. This is pretty important, I think. So let me go on and we'll mention that. This one. Assuming that the gradient is not the zero vector. Okay, let's get that out of there. Can't do that. If it is, don't do anything else with it. Let u be a unit vector making an angle of theta with that gradient, that non-zero gradient vector. Then that directional derivative in the direction of u of that gradient of this function, scalar function p of f evaluated at fp, is going to be the magnitude of f, the gradient of f of p times the cosine of the angle. The other magnitude you would expect to see is the magnitude of u, which is 1. Okay? So this gradient of f of p points in the direction of maximum rate of increase of f at p, negative points in the maximum rate of maximum rate of decrease at p, and gradient f of p is normal to the level curve or the surface f of p, which means it's on that maximum. Okay, so those are just a few things to note. There's an example. There's a level curve p, the little green curve, level curve of alpha of x. At that point p, the gradient function always points maximum amount of increase. And I was going to talk some about the direction of it, but let's not. Okay, here's, say, that same curve we were looking at as a family of curves, contour map of that function. Here's a 24, 25, 26, and 27. And when you do the gradient of this in the direction of u here, you almost have to do the example to see it, but it is the direction of maximum increase. You see, you're going from 24 to 2450 to 25 to 2550, 26, 2650. So increasing going in that direction, and at this point P, take your perpendicular to the tangent line there, maximum rate of increase, that's your gradient vector. Now if you do the directional derivative u, if that gives you the component of this in that same direction of u. But almost have to have the problem to realize it. There's a physical example of that. And the gradient as a normal vector, some interesting fun problems, but just not enough time to do them. Okay, of a surface like this and increasing going outward, the gradient is going to be tangent to this and perpendicular to in both directions. Normal to the surface. Perpendicular, normal, that means the same. All right. I wanted this to go a lot faster, but these are concepts I'm afraid you run into in engineering and other places. You just need to have at least a little cursory information of what they're talking about. Why is it every time it gets to this point? That one did open, the other one didn't. Okay. What we have here is a function, a scalar function, f, with 3 independent variables. Okay. And each of these let me back off. This function f is a function in 3 variables, x, y, and z. But each one of those variables is a function of 2 parameters, s and t. Okay? So basically, the s and t become your independent variables. The f may represent, say, w or something else that is your ultimate dependent variable. But you have then these intermediate variables here that are not quite in. For f, they're the independent variables, but for themselves, they're the dependent variables. So it makes for an unusual situation, but this is how nature is, okay? So it's not something someone's making up. Okay. There was a goodness, I can't get this to click. There we go. Now, here is the chain rule in that situation that we just had. A scalar function of 3 variables, but each of those variables is a function of 2 independent variables. So those 3 are sort of intermediate type variables. So what we're doing is taking the partial of that scalar function f with respect to s, which was the independent variable. F is not a function directly of s, but through the intermediary things, x, y, and z. So how do you do that? You do the partial of f with respect to x. You know what that is. Okay, I mean, you can calculate that. Then multiply that by the partial of x with respect to s. Now this looks like one we had earlier, where those were actually derivatives. That's when you had a single independent variable. Here you have 2, so you have to have that as a partial. And plus the partial of f with respect to y, the partial of y with respect to s, plus the partial of f with respect to z, plus the partial of z with respect to s. And this then gives you the partial of f with respect to s. A scalar function, a partial with respect to an independent variable, and if you sort of look at this, if you think of the partial of x's going out, that would give you partial of f with respect to x in the y direction and in the z direction. So it basically expands what we were doing, but now in 3 dimensions. Now this is with respect to s, so this has to be the ultimate independent variable. But there's 2 of them, so the other one is with respect to t. And it follows exactly the same pattern that the partial of f, the bigger function, with respect to t is partial of f with respect to t, x. Remember, that's your outer function, and then partial of x with respect to t is your inner function. And then you do the same thing for partial of f with respect to t, dx, dy, dt, and then the partial of f with respect to z, dt. Okay. So that's basically your rule for chain rule in multiple independent variables and with or without intermediate variables. Okay. Here then it's the general version of the chain rule. Well, why did it do that? Sorry, this is taking longer to set up than I thought. Like I told you earlier, didn't get all of lunch and I feel like I'm running low right now, blood sugar or whatever. Okay. The general version of the chain rule is f is the scalar function of multiple variables. Okay? Now we quit doing x, y, z, x1, x2, x2. The differentiable function of n variables, but each of those variables, each one of them is differentiable function of m independent variables, t sub 1, t sub 2, t sub 3 up to t sub n. This is for really complicated looking situations, especially n and m are fairly large numbers. But take the partial of your overall function, that scalar function, with respect to any one of these independent variables, okay? And that would be the partial of f with respect to the first of your intermediate variables times the partial of that intermediate variable with respect to this one, plus the partial with respect to the second with respect to the other. And you keep on going down until you have every one of these x's there, x, y, z, whatever they happen to be, one term for each of those, beginning with the partial of f with respect to the first, then that partial of that with respect to the tk. So you begin and you end with what you started, and you put each of the intermediate values in between. I mean, that's one way to look at it. General version of the chain rule, as generically stated as possible. Okay. Now, another way to look at that, and I think we did this before, maybe only in 2 dimensions, was like this. It turns out being a dot product between, guess what that is? Your gradient function. Partial of f is a vector gradient, and then this is your also a vector, and that's your path, right? Partial of x1 with respect to t sub k, partial of x2. Only with respect to that variable there. That dot product, this times that, this times this, plus this times this, and that gets you back down to your scalar value because that's a dot product. So there's your most generic form, I think, perhaps. Okay. I think this is a specific problem, so we'll just skip over it. And this is an important conclusion of implicit differentiation. And since we don't have time to do it, I won't go into gory detail about it. Okay. In fact, I don't really want to go into any detail about it, I don't think. Let's see. Let's just leave it. It would take way too long to try to explain all that. So let's keep going. There's a pretty good example and another one. And that second one was for assumptions matter. Okay. All right. Sorry, this is really helter-skelter, but I wanted you to at least see things like gradient and get just sort of a general idea of what that is. No, this is optimization. I think I'll skip this completely. And let's see what that last section is. No, Lagrange multiplier. I'm not going to do that except for this. Okay. I will. Well, y'all don't need it, but I will do it for the one. Get out of there. Okay. This is some pretty interesting stuff. It's a follow-on to optimization. So if we didn't do optimization, it makes no sense to do this, except that here, Lagrange multipliers. Okay? And later you might really actually run into something called Lagrangian. That's what you use for optimization. But you're going to take a whole course on that, so I'm not going to go over it here. But if you keep your books, then you might want to go back and refer to these if you get there, okay? And that's all I'll say. The one person who hasn't done a paper, Lagrange is a great potential paper topic. Who was he? How did he develop these? What are applications? And the applications are enormous, okay? So that was basically all I was going to do on there. There's an economist, Paul Douglas, working with mathematician Charles Cobb. So either one of them would probably be good paper topics. Fitting data with relationships between labor, capital, output of industrial economy. So that's the kind of stuff you use. Industrial engineering, this you use all the time, all over the place. I don't think any of you are going into that, but if you are, you would use that. Okay, I think that's it for the chapter. Okay. So, let's get out of that. Didn't mean to take that long, but I want to get the 15. Now, 15 is actually really easy. Once you've got the partial derivatives down, doing multiple integrations just follows exactly like you would expect it to. And I think I'm going to hit this first section pretty rapidly just to give you the concept of it, because I think it's the later sections that actually have the really how to. I don't even want to spend any time on things like this, but let's just do it quickly. Yeah, it went right past it, didn't it? I think in the Silva's book, she'll see this illustration. Rice terraces illustrate how volume under a graph is computed using iterated integration. It's close to that. The one in the current book, the current edition, has a little, it's another picture, but not quite as steep a hill that they're doing it on. So basically what we get down to is integration, multiple integration. You basically have a surface, you're integrating under that, finding out the volume under the surface. Not the area under a curve, volume under a surface. And then you pick out a domain, D, and then you get basically the area of the surface and then times the height of that. So your Z is a function of alpha of xy. Alpha of xy depends on what domain you have there. So it's that kind of a concept. The simplest of those domains is a rectangular domain, dx, dy, okay? And that gives you your, rather than call it domain, then we call it rectangular domain. Okay? The R is a rectangle. A to B on x, C to D on y, okay? And you do the area under that, or the volume under that area that you got up above. Sorry. I can tell I didn't drink enough water. I'm getting awfully dry. So here is, say, one of those rectangular domains. I don't want to do too much on this because it's a little tedious. you're integrating some shape up here over this domain R, and this is A to B on X and C to D on Y. That. So we break that into a grid. In that grid, you have n columns, m rows. This happens to show 5 columns and 4 rows. It doesn't matter. What you're going to do is let the delta X and the delta Y, they don't have to be really all that much related to each other. Here they look like they're the same. They don't have to be. But that gives you a portion of this in every one of those grids. Okay? And you can take the value at any point in the grid and multiply it by the area of the grid. The points can vary there. What you're going to do, of course, is take smaller and smaller delta x's, smaller and smaller delta y's. They get down to dx's and dy's, infinitesimally small, and then basically you don't have a single point basically on those. Integrate over all that. Okay? So it's the same kind of deal whereas we used to break a partition of your function into dx's and then do your y dx, y being some curve up here. Now we've got z, the surface up here, broken into xy portion of the domain, rectangular domain, and then you're going to let this delta x as the number of columns gets larger, the thickness gets smaller, and that's approaching a dx, and that's approaching a dy. And you have the value of the functions at each of those. Just like we used to do with Riemann sums, basically. And that's showing here is the area under a curve. You could approximate that by areas from some point under some sort of a partition that you have of that. That's a Riemann sum. And you see this area is that you're calculating here, undershoots, overshoots a little bit, undershoots, yeah. So it's not a bad approximation, but the smaller you can get your increments there, the better your approximation. Same thing here. This is breaking this into a delta y and a delta x. Here it's 1, 2, 3, 4, 5, 6 and x, 1, 2, 3, 4, 5, 6 and y. And then you have a single column here evaluated at that point, and then times that area. That will give you your volume. Sum all of those up, from A to B on x's and from C to D on y's, and then you've got your total volume, or at least an approximation of it, which is probably just about as good as this was. Some of these overshoot a little, some corners undershoot, whatever. You just let your delta x's get smaller and smaller as the number of increments get larger and larger, and therefore you're going to approximate a thing. So again, we call them Riemann sums. So this is just to be complete here. The limit of the Riemann sum, and this sum now has two suffixes, n for the number of increments in x, m for the number of increments in y. For some reason, I've never figured out why they do n rather than mn. It seems like if you do it xy alphabetically, you would do this too. It doesn't really matter. We don't really use those. But you're letting that Riemann sum approaches a limit L as your partition. That's what the P stands for, partition of any square that you have in there. A little rectangle you have in there is approaching 0. That means your n and m are getting bigger. Your delta x's and delta y's are going to dx and dy. But that's as approaching the Riemann sum approaches that limit L as your magnitude of your partitions are approaching 0. If for all epsilon greater than 0, there is some delta greater than 0 such that the difference between your limit and your Riemann sum, if you can keep that less than epsilon, there is a delta that will keep that less than epsilon. For all partitions satisfying the partition, it's approaching 0, but as long as it's less than this value delta. and all choices of the sample point. Doesn't matter where you choose that point to measure. Okay, that's your technical definition of Riemann sums. In reality, we really don't use that, but here's an example. Here with M on the X is 4. I'm sorry. N on the X is 4. Well, they have them backward. M on the Y is 6. And you're going from 0 to 2 to 0 to 3, so it breaks it up pretty nicely. So these are all squares down there that your partition is done. But this is not a very precise estimate. But if you go to M equal 12 and N's equal 8, you just double the number of partitions here. Boy, look how much finer you get. Then they ran this up to, see, this is, you had 3 difference here, and this was 2 per unit, this is 3 per unit, and 4 per unit, 2 per unit, and 4 per unit. This one is, let's see, 10 per unit, okay? So that would be 30s and 20s. So you really ramped it up, and boy, you got something pretty close to the exact thing. Well, you just let that go to infinity, so your delta x and delta y becomes dx and dy. So the midpoint approximation under that, I guess maybe we ought to do that example. Is it time? Yuck! We didn't do a single example in the chapter I thought we'd be focusing on today. Let's see where that is. Goodness, I don't even see this. There it is. Okay. All right, we'll start next time and actually do a few. In fact, we'll do several. We'll start on page 823. And since we didn't do any examples, there's not really a lot you can do on your homework exercises except, maybe do a few Riemann setups and see what you can do with that. But we will do those later. The actual double integrals and more general regimes, that's 15.2. We'll go and get into that, and that'll do double integrals and triple integrals. That's most of what your questions on the test will be. Maybe a little bit here, but that's going to be mostly what they'll be. And then triple integrals in 15.3, if we can get that far, we'll try to do those as well. I thought they had some triple integrals in 15.2 there, but but we'll see. We'll get as far as we can. I'll try to have, get to you. And do you need yours early, or is Wednesday going to be fine?
I mean, whenever you can.
Okay.
The sooner the better.
Okay. Yeah, because I know you got 2 classes of them. So, yeah, I just don't have the stuff here now. But I can maybe piece something together for you now and type it up, pull them together in a nicer form by Wednesday. Okay. All right. We were missing Faith. All right. Now, I need to do here is in this